You prompt an artificial intelligence, and it responds with an instant cascade of complex Python scripts and essays. The speed creates a compelling illusion. It looks exactly like a machine thinking. The reality is strictly mechanical. Traditional large language models are highly advanced statistical mirrors. They operate on reflex, executing autoregressive next token prediction to guess the most mathematically probable word, millisecond by millisecond. Because this architecture is a forward-moving reflex, it prohibits internal correction. A standard LLM cannot evaluate a logical misstep until the incorrect token is already permanently printed to the screen. This reflex mode works for writing emails or translating text, but it fails when applied to multi-step logic problems, like auditing financial ledgers or debugging race conditions in a dense codebase. To solve high-stakes engineering problems, speed is a liability. The underlying architecture has to prioritize verifiable correctness over immediate generation. Psychologist Daniel Kahneman established human cognition has two distinct modes: an automatic mechanism called System 1 and a deliberate logical process known as System 2. Traditional LLMs are the digital equivalent of System 1. They are fast, automatic, and structurally incapable of taking a pause. Large reasoning models bring System 2 into silicon. Instead of pushing inputs directly to outputs, an LRM diverts the input into a deliberation layer. Inside, it pauses generation, initiating a hidden loop to plan, simulate, and cross-examine its logic before finalizing a word. By decoupling the prompt from the immediate output, LRMs create a separate dimension of computation where actual reasoning takes place. This hidden cognitive sequence breaks down into 4 rigid mechanical stages: planning, execution, verification, and synthesis. During the planning stage, the model refuses to guess the final outcome. It forces a complex query through a systematic breakdown, dividing the problem into a sequence of small, manageable computational steps. To prevent hallucinating facts, the verification stage natively routes intermediate steps through external tools, dropping an algorithm into an isolated code sandbox to see if it compiles. The LRM runs scripts and queries databases, extracting hard empirical facts before allowing the neural network to proceed. By anchoring intermediate steps to rigid classical computation, the model discards statistical guessing. It builds a traceable, fully auditable chain of thought. Building this architecture requires answering a difficult engineering question. How do you mathematically train a statistical predictor to value logical integrity over conversational fluency? It starts with reasoning-focused fine-tuning. Engineers feed the model massive datasets of logic puzzles and multi-step mathematics. The key is that these datasets map out the explicit, step-by-step chains of thought required to reach the solution. When evaluating a 50-step derivation, grading only the final answer means a fatal error at step 3 goes unnoticed. The solution relies on process reward models, acting as automated AI judges deployed during reinforcement learning. A process reward model scores the mathematical and logical integrity of every individual step independently. This prevents the primary model from memorizing correct answers built on flawed logic. This reinforcement ensures the model prioritizes pathways that lead to verifiable logical consistency, rather than just generating a plausible-sounding sequence. The core engine that powers this logic in deployment is inference time compute. This is the exact computational budget a model is allowed to burn after you hit enter. Standard LLMs expend a static amount of compute, using the same mathematical energy to draft a social media post as analyzing a nuclear reactor. This chart shows how an LRM dynamically scales its effort. It maps problem complexity against the inference compute budget. For simple requests, the budget stays flat. For difficult requests, the compute allocation scales upward. During this extended compute phase, the model executes a tree search, initiating multiple simultaneous chains of thought. When a logic branch hits an internal contradiction, the model triggers backtracking, shutting the dead-end branch down and allocating compute energy to an alternative route. Inference time compute turns the model into an active experimenter. It tries, fails, and corrects itself in a hidden environment before presenting a single word to the user. This level of freedom introduces an immediate engineering hazard. A model given permission to think endlessly will spiral into infinite loops, burning server time and compute budget. To prevent this, architects implement a structural safeguard: adaptive reasoning suppression. Adaptive reasoning suppression acts as an internal certainty monitor. It constantly evaluates the logic tree for diminishing returns and trims away redundant branches the moment a high-confidence path is established. This safeguard drives down token usage and cuts latency without sacrificing the accuracy of the final output. Architectural elegance in an LRM requires teaching the model how to think deeply and then hardwiring it to know exactly when to stop. The cognitive depth of large reasoning models introduces harsh physical and operational realities for engineering teams. Generating thousands of hidden reasoning tokens per query demands amounts of VRAM and raw electrical power that standard LLMs never touch. This creates the primary deployment friction: latency. Because the LRM must complete exhaustive hidden tree searches and verify its sandboxes, final answers can take 45 seconds to several minutes to generate. That latency disqualifies LRMs from handling real-time applications. You cannot use them to power fast-paced consumer chatbots or instantaneous translation services. Deploying an LRM is paying a premium in time and hardware to guarantee factual truth. Paying that premium to summarize an email is a misallocation of resources. Enterprise software now relies on hybrid routing architectures, eliminating the need to choose exclusively between speed and deep logic. Every incoming query first hits a complexity analyzer. This node scans the prompt for specific operational markers, looking for words like trace, debug, or verify, as well as highly dense mathematical formatting. Prompts scoring below a predetermined complexity threshold are instantly pushed to a fast, cost-efficient LLM. High-stakes, high-complexity prompts are diverted the other way, triggering the heavy compute budget of the LRM. This routing logic ensures that engineers only pay for expensive deliberation when the problem mathematically demands it, keeping the user interface responsive for everyday tasks. Building for reliability requires orchestrating these two modes. By managing the allocation of test-time compute through hybrid routing, developers can ensure that high-stakes problems receive the deliberation they require, while maintaining the efficiency of reflexive models.